Hi everyone. In this video, we want to take some time to explore series that contain both positive and negative terms in the series, in particular examining absolute and conditional convergence. In a previous video, we looked at a number of convergence tests, many of which only applied to series with positive terms. We saw that in those cases, the series that contained only positive terms yielded sequences of partial sums which were monotone. And in many cases, we were able to take advantage of that monotonicity in order to prove convergence results. However, when series contain both positive and negative terms, we can't always conclude monotonicity, and therefore we may need to be more careful in our analysis. In particular, we'll re-examine the topics of absolute and conditional convergence, which we explored in our earlier short run-through of some of the calculus topics in the first couple of lectures in this course. And then we will explore the Riemann rearrangement theorem, which shows us the wide variety of possibilities for conditionally convergent series when their terms are rearranged. So to begin, let's first just recall the definitions of absolute and conditional convergence. So we say that a series AN is absolutely convergent if the series absolute value of AN converges. If the series AN converges, but the series of absolute values diverges, then we say the series AN is conditionally convergent. So to make sense of this, we'll work through a couple of examples in a moment, but let's first notice a couple of things. So here we're saying that this series is absolutely convergent if this series converges. But notice we haven't said anything about the convergence of this. It turns out that if the series of absolute values converges, the original series must converge. That's something we will look at in just a moment. In the second part, right, we see, however, that it is possible, the implication is only one way, so it's possible that this series converges, however, the series of absolute values diverges, and in that case, we call the series conditionally convergent. So let's first look at this corollary. It says, if the series sum of the absolute values of ANs converges, then the sum of the ANs must also converge. So this follows, it's called a corollary because it follows almost immediately from the Cauchy criterion for series convergence. So since the sum of the absolute value of the ANs converges, then the Cauchy criterion says that for any epsilon greater than 0, there exists a natural number capital N such that whenever little n is greater than or equal to m is greater than n, capital N, we have that let's make this index this sum over k equals n to m, that this is less than epsilon. Okay, so this orange part here, this is just by the Cauchy criterion. Okay. All right, well, if I look at this, the first thing I notice, I could actually drop these absolute values. So I'm adding up, this is a finite sum of positive terms. This sum has to be positive. So I could just as easily just drop off these absolute values. Okay. And now again, this is just a finite sum. Okay. So now by the triangle inequality, if I look at the sum k equals n to m of the ANs without absolute values, that must be less than or equal to the sum k equals n to m of the absolute values of the, I'm sorry, I keep writing ANs, these should be AKs. Okay, right, but this is just saying I have the absolute value of a sum of a bunch of things that's less than or equal to the absolute value of each term and then sum them all together. And so combining this and this, right, we see that the sum k equals n to m of the AKs in absolute values, that has to be less than or equal to this, which is the same as that, which is less than epsilon. Okay. But this is just saying that the series AK satisfies the Cauchy criterion. And so by the Cauchy criterion, the sum of the ANs converges. Yeah. And again, just remember, these are called Cauchy criterion because these are really just checking that the sequence of partial sums is Cauchy. And we know a sequence of real numbers is convergent if and only if it is Cauchy. Okay? So this Cauchy criterion is an if and only if. Since this series converges, this criterion is satisfied. Since this criterion is satisfied, which is really saying the sequence of partial sums is Cauchy, then this series must converge. Okay, so looking back then at our definition of absolutely and conditionally convergent, we see that there's really no reason for absolutely convergent. As soon as we say that the sum of the absolute values converges, that automatically implies that the sum of the ANs converges. So there's no need to say both. Whereas when we're talking about conditional convergence, there we need to specify that we're really thinking about the fact that the sum of the ANs converges, but the sum of the absolute values does not. So now, just to solidify this a tiny bit more before we continue, we want to next look at a couple of examples, again, just to help us make sure we're comfortable with these competing notions of absolutely and conditionally convergent. All right. So let's look at two examples here. So with each of these, the first thing I'm going to do is I'm going to look to see if they're absolutely convergent. Okay. So if I look at this series, if I look at this, so and we can assume for both of these that these are sums from n equals 1 to infinity. So this is, if I take absolute value, minus 1 to the n plus 1 over n, I see that this really just becomes what? This is the sum n equals 1 to infinity. So the absolute value of minus 1 to the n plus 1, well, minus 1 to the n plus 1 is just going to be 1 or negative 1. And in either event, when I take absolute values, I just get 1 over the absolute value of n. But n here is a natural number going from 1 up to infinity. It's always positive, so its absolute value is just n. So we get this series, right, which is the harmonic series we've seen before, which we know diverges. Okay. Now, note that that doesn't tell me that this diverges. That just tells me that the sum of the absolute values diverges. So now I need to go and check this actual series on its own. Before I do that, let's look briefly at this. So here, if I take absolute values, sum n equals 1 to infinity of absolute value of minus 1 to the n over 2n squared plus 1. Well, let's see, when I look at this, I get that this is equal to the sum n equals 1 to infinity of absolute values, that'll be 1. This is always going to be positive. Okay. Now, immediately, I might not know what happens here, but if I look at this, I can make this larger by making the denominator smaller. So one way I can make the denominator smaller is to get rid of that plus 1. Okay. Another way I can make that denominator smaller is to get rid of that 2. Okay. And this is now a P series with P greater than 1. So this series actually converges. Okay. So now here actually I'm done. I know that the sum of the absolute values of each term converges. That tells me by the corollary we just proved that this also converges. And so for this series, I know that this series converges absolutely. Okay. For the time being, with this series, I'm still unsure, right? Because I know it doesn't converge absolutely. That doesn't tell me that it doesn't converge, though. It may just converge conditionally. Now, this is where we could apply another series convergence test that you likely saw in a Calc 2 course. So this would be the alternating series test. The idea here is you need to check two conditions. So to apply the alternating series test, what I do is I look at this and I really want to identify the non-alternating part. So in this case, that's like the 1 over n. This is 1 over n times this term that's alternating back and forth between +1 and -1. And then here I need to show that two things are true. The first is that the series is decreasing. Okay. Here that's clearly true. As this gets larger, the whole thing gets smaller. So that works. And then I also need to make sure that these are not just decreasing, but they're decreasing to 0. Clearly 1 over n is going to 0. And the alternating series test says, well, if both of those things are true, then this series converges. Okay. So here we have that this series converges, but the sum of its absolute values does not converge. So for this series, right, we would say that this converges conditionally. So, great. We have these definitions. We have this terminology. I think it's really easy, especially the first time you see this, to think, okay, no big deal. Like I very much thought the first time I took a Calc 2 course that this was just like some extra jargon that was invented by big math to sell more textbooks, right? Like, it was just some terminology that we could use so that the teacher could ask more questions, right? But it turns out that well, there are a couple of reasons, but one really important reason to care about the difference between absolutely and conditionally convergent series is that when you start trying to rearrange terms, they behave very, very differently. Okay? And so to see that, let's look at the following. So let's look at this example, but now just on its own. This is conditionally convergent. Let's look at this in a little more detail. Okay. Now, I cautioned at the very beginning of our discussion about series, I cautioned about thinking about these things as infinite sums, right? I said you really should think of these as the sequence of partial sums, because if you think about them as just infinite sums, you can be led to try and apply some things incorrectly. So in this case, what we want to do, though, is sort of ignore that for a minute. Okay. So if I look at this, so if I just start writing out terms, when n is equal to 1, I'll just get 1. Then I'll get minus a half. Then I'll get plus a third, minus a fourth, plus a fifth, minus a sixth. And I'm just going to write out a few more terms. Okay, you get the idea. So on and so on. Okay. Now, we know this converges. We actually don't know what it converges to, but I'll actually go ahead and tell you this converges to the natural log of 2. Okay. So you think, great, no problem. All right. Well, let me start rearranging the terms in this sum. Okay. So I'm going to do this in a very particular way. Okay. So I'm going to rearrange this by, I'm going to leave these first two alone. Then I'm going to move this 1/4 up. Okay. And then I'm going to add in 1/3, and then I'm going to pull this minus 1/6 here, and then I want to do minus 1/8. And then I want to do 1/5 minus 1/10, and then minus 1/12. Okay. And I'm writing dot, 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 and you might be saying, like, I don't understand, like this doesn't seem like the same sum. Like, where is 1/9? Okay. Well, somewhere out here you'd have a term that would be 1/9 minus 1/18, and then you'd have like minus 20 or something. In general, what I'm doing here is notice that here are all the odd terms. So there's 1/1, 1/3, 1/5. The next one would have a 1/7. And then I'm doing minus half of that term. So I have 1 minus a half. I have a third minus a sixth. And you might be saying, wait, how do I know, right, like, how do I know I get a sixth here? Right, it's 1/3 times a half. It's half of that. 1/5 minus 1/10. Well, that's half of that. Okay. And then each of these are minus the multiples of 4, right? Now, what's hard to see is, how do I know that every term that was up here appears down here? Well, it turns out that every one of these denominators is either odd, so all the odd ones will show up at the beginning of one of these parentheses terms. So that takes care of all my odd terms here. Okay. Of the remaining terms, they fall into one of two categories. They're either multiples of 4, in which case they'll appear here. If they're not multiples of 4, the only things that are left are things that are even but not multiples of 4. That means they must be twice an odd number, the denominator. So 2 is twice an odd number, 6 is twice an odd number, 10 is twice an odd number. So that covers all the rest. Okay. And so you go, okay, well, great, no big deal, but I mean, this is just sort of some silly rearrangement. If I then do this, let's see, 1 minus a half, that would just be a half. 9 minus a fourth plus 1/3 minus 1/6. That's 2/6 minus 1/6. That's just 1/6 minus 1/8 plus 1/5 minus 1/10. So that's 2/10 minus 1/10. That's 1/10 minus 1/12. Okay, so on and so on and so on. And then I look at these and I go, oh, look, okay, all these things are even. Let me factor out a 1/2. When I do that, I'm left with 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6, so on and so on. And then I look at this and I say, well, wait, this is that. Right? So this is the same as that, but that's equal to natural log of 2. So this must be equal to 1/2 of natural log of 2. Now, if you'll notice here, I've been a little deceptive. I did not write an equal sign here. Okay. And the reason I didn't write an equal sign here is that this is clearly not equal to this, right? Even though these two sums have all the same terms, they've just been rearranged. So what we see is that when we have a conditionally convergent series, rearranging the terms may result in a different value for the sum. Okay, so here it's called conditionally convergent because the order of the terms in the series is incredibly important to determining what you actually converge to. The same is not true for absolutely convergent series. Absolutely convergent series, you can rearrange the terms however you want, and they'll always converge to the same thing. And so one of the reasons this distinction is so important is because absolutely convergent series, we really can treat them like infinite sums. We can rearrange terms, we can associate terms in different ways, and nothing bad happens. Here, the problem is that we've tried to, really what we've done is we've applied commutativity and associativity an infinite number of times, which are not really valid uses of commutativity and associativity. They apply like in general, they only apply to finite sums. So we can't really do this for an infinite sum, and that's why we end up with this different value. So here, if you rearrange the terms in this series, in the arrangement that's presented here, you just get natural log of 2. In the arrangement that's presented here, I get 1/2 natural log of 2. All right. So in a way, these are sort of distinguishing, absolutely versus conditionally convergent is in a way distinguishing between nicely behaved series and, well, from this example, you might just go, oh, okay, maybe they're not so nicely behaved. Okay. Now, you might wonder, how far can you take this, right? You might wonder, like, okay, he took this series, which converges to natural log of 2, and was able to rearrange it to get half of natural log of 2. You know, maybe that's the case. Maybe every conditionally convergent series, you can rearrange it so you get half of the value. It actually turns out it's much, much worse than that. Conditionally convergent series are very badly behaved. Okay. In fact, they're so badly behaved that a conditionally convergent series can be rearranged to give you any sum you would like, or not to converge to anything at all. Okay. And that sort of astounding fact is what's called the Riemann rearrangement theorem. So we want to conclude this video by looking at the Riemann rearrangement theorem and then at least outlining the proof. So the Riemann rearrangement theorem says let AN be a conditionally convergent series and let M be some real number. Then there exists this bijection. So we're going to call this bijection sigma. It's a bijection from the natural numbers to the natural numbers. Now, let's pause for a second. This sigma is often also called a permutation, because the idea is it takes the natural numbers and it reorders them, right? So sigma might take, it goes 1, 2, 3, 4, 5, 6, so on and so on. And then you can imagine another copy of the natural numbers down here. And this sigma, it's a bijection, so it's 1 to 1 and it's onto. So it might take 1 to 3, but once 1 goes to 3, nothing else can go to 3. If something else went to 3, then it wouldn't be 1 to 1, okay? And it wouldn't be a bijection. And now maybe 2 goes to 1 and 3 goes to 2 and 4 goes to 4, 5 goes to 6, maybe 6 goes to 15, 52 goes to 5. But the idea is, one way to think of this is just it's a reordering. So so now the first term is now 3. The second term is now 1. The third term is now 2. The fourth term is still 4. The fifth term is now 6. The sixth term is whatever, 52, and whatever's up, 17 is now the fifth term. Okay. So the idea is that this map sigma gives you a permutation of the natural numbers. It's telling you how you're going to rearrange your series. And so what the Riemann rearrangement theorem says, there exists a bijection, there exists this rearrangement such that when you rearrange the terms in the series, so now you're adding up the A sub sigma of n's. So these are all the same terms that were in your original series, just reordered. You can make this series converge to M. Okay. So let's think about that for a second. We're saying for any real number, you can find some rearrangement of the terms so that your series converges to that real number. So we saw a conditionally convergent series that converged to natural log of 2. We saw a rearrangement that gave us 1/2 of natural log of 2. But what this is saying is there's some rearrangement that gives you a value of pi, and there's another rearrangement that gives you a value of 43, and there's another rearrangement that gives you negative pi to the 100th power divided by 17. For every real number, there is a rearrangement of the terms of your series such that the sum of those rearranged terms gives you that real number. Okay. What's more, there also exists a rearrangement such that when you add all these terms together, you get positive infinity, or you get negative infinity, or you fail to approach any limit at all, whether finite or infinite. So really, anything is possible when you start rearranging the terms of a conditionally convergent series. All right. So I mentioned I want to at least sort of sketch out this proof. Um, I will post in the course resources a handout that has a full written out version of the theorem. I think this is a prime example of a theorem that is actually a little easier to explain and understand than it is to write out, just because some of the notation can be a bit dense. So let's sort of talk through it. So the first thing we want are just a few sort of facts about convergence, about conditionally convergent series in general. Okay, and the idea is really is that really there are three important facts. So the first fact is that so if you take this series and you break it up into sort of the positive terms and the negative terms. Okay, so let's start. So I'm going to define a sub n plus. That's going to be a sub n if a sub n is greater than or equal to 0, and 0 if a sub n is negative. And I'm similarly going to define a sub n minus to be 0 if a sub n is greater than or equal to 0, and a sub n if a sub n is negative. So then if we look at the series, so let's think about this series for a second. This is the series that contains only the positive terms. Okay. Basically, what it's done is it's kept all the positive terms and it's turned all the negative terms into zeros. Okay. And so what you get here is that this sum diverges to positive infinity. And if you look at the negative terms, that series diverges to minus infinity. Now, there's really sort of two facts going on here. The first is that any conditionally convergent series must have an infinite number of positive terms and an infinite number of negative terms. Okay. The second piece then is that once you know that, you can show that the sum of those infinite number of positive terms must diverge to infinity, and the sum of those infinite number of negative terms must diverge to minus infinity. Okay, so I wrote one here, but I think in the notes, these are really sort of labeled as facts 1 and 2. So the first is that there are an infinite number of positive and negative terms. The second is that these sums diverge to positive and negative infinity, respectively. Okay. The third fact is simply, this is a fact about any convergent series, actually, not just conditionally convergent series. But if this series converges, conditionally or absolutely, then the limit of the terms must go to 0, right? This is a pretty easy proof by contradiction, right? If the limit of the terms did not go to 0, then it would be sort of like you were adding up an infinite number of non-zero terms, which would have to diverge. Okay. So these are just sort of a few facts that we need, and in particular, we need that these sums diverge to positive and negative infinity respectively, and that the limit of the terms must be 0. All right. So once we have that, we then set about constructing the rearrangement of our series that we want. And so, okay, let's imagine we have a real number m. Okay, we're going to take our real number m. All right, and what I'm going to do is first I'm going to choose a natural number p1 to be the smallest natural number such that the sum k equals 1 up to p sub 1 of a sub n plus is greater than m. All right, let's, to help us understand what's going on here, let's go back to that series sum minus 1 to the n plus 1 over n. So if we just wrote out the terms here, right? This was 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6, so on and so on. Okay. And so the idea is this P1 is really saying, figure out how many terms you need to take. And here we're really only counting the positive ones, right? So all my negative terms will be made 0 by this little plus operator here. Okay. So if I look at a sub n plus, that's going to be 1 plus 0 plus 1/3 plus 0 plus 1/5 plus 0, so on and so on. And figure out how far out you need to go until that sum gets greater than whatever your m is. So if your m, for example, was, say, 3/2, you would need to go out 1, 2, 3, 4, 5 terms, because by the time you go out 5 terms, you would have 1 plus 0 plus 1/3 plus 0 plus 1/5, and 1 plus 1/3 plus 1/5 is just a little bit greater than 3/2. Okay, so what you do is you basically figure out, okay, I'm going to take my positive terms, right? And I'm going to rearrange them so that I have 1 plus 1/3 plus 1/5. And yes, technically I have some zeros in there too, but who cares about the zeros? Okay, so that's how I'm going to choose P1. Now I'm going to choose P2. So, or sorry, I'm going to choose not P2, I'm going to choose Q1. It's going to be a natural number. And I want it to be the smallest natural number such that, all right, now the idea is I've taken this sum, k equals 1 to p plus 1 of a sub n plus. So I've taken positive terms until I got above m. And now what I want to do is I want to add in some negative terms. How many of them? Well, I'm going to go up to Q1 of the negative terms until I get just below m. Right? So the idea here is you add up positive terms until the fact that this is the smallest natural number that satisfies this means you stop as soon as you cross over in m. So like in this case, we stopped the second we had added enough to go over 3/2, we stopped. Now you start adding in negative terms, but you add in negative terms now until you get just below your m value. So in this case, if I start adding in negative terms, I'm just going to get a minus 1/2. And now this whole sum is back down below 3/2. Okay. And now I'm going to repeat this. Okay. So I'm now going to sort of keep iterating this process. And let me so now iteratively choose p sub I plus 1 to be a natural number, to be the smallest natural number such that, okay, so now what I want to do is I want p sub I to be the one that takes me back above m. So it's going to be the one so that the sum k equals 1 up to p sub I plus 1 of a sub n plus the sum k equals 1 of q sub I of a sub n minus gets me back above m. Okay. So again, for p sub 2, I would basically say, okay, p sub 1, those positive terms took me above m. Then I added in q sub 1 negative terms. That got me back down below m. Now I'm going to add in p sub 2. Well, I'm actually going to add in, I guess, p sub 2 minus p sub 1 plus 1 more terms, right, to get me back above m again, to get this sum back above m. And then I would choose q sub I plus 1. And I'm going to put dot, dot, dot to be the smallest natural number such that we get back so now I'm going to take my negative terms up to q sub I plus 1 of a sub n minus, and that's going to take me back down below m. So the idea is I just keep adding in little bits of positive terms, negative terms, positive, so that I go, my whole sum is going just above m, just below m, just above m, just below m, just above m, just below m, so on and so on and so on. Okay. Now, in doing this, what I'm really doing is I'm redefining, I'm really reordering the sequence of my terms. So the idea is I can rewrite the terms in my series then as sort of, so A1 all the way up, or A1 plus all the way up to A sub P1 plus. So these are all the positive terms that when I added them together, they took me above the value M. Then I started adding in, then I started adding in negative terms. So A sub 1 minus up to A sub Q sub 1 minus. All right, then I need to add in some more positive terms. I'd already gone all the way up to P1, so I'm going to start at a P1 plus 1, and then I'm going to keep adding in until the total value of my sum goes over M again, and that'll be at P sub 2. And then I just keep doing this. I keep sort of adding in positive terms to get me above n. But notice this gives me a rearrangement of the terms in my series. And so my claim then is that this rearrangement, so I'm not going to formally define what sigma is, like writing down exactly what this bijection is would be a little difficult. But my claim is that by rearranging the terms in this way, then this converges to M. Okay. Now, I'm not going to write out the proof here to show exactly that converges to M, but fundamentally the idea is that each time I'm getting just above or just below M, right? As I add in these sort of P blocks and Q blocks of positives and negative terms, each time I'm getting just above or just below M. And the amount that I'm getting just above or just below M by is a term in my series, right? But those terms are getting smaller and smaller. So each time that I sort of switch directions from going above to below or vice versa, the amount that I'm going above or below by is getting smaller each time I cross. And so the difference, as I go further and further out in my sequence, the difference between M and the values in my sequence of partial sums is getting smaller and smaller and smaller. So I am, in fact, approaching M in the limit. Okay. So again, to see a full detailed proof of that, you can see the notes. And then it turns out that you only need to make slight modifications to these ways you chose P and Q in order to prove the rest, to show that you could find a rearrangement that diverges to positive or negative infinity, or to show that you can find a rearrangement so that your series doesn't converge at all. Okay, so this Riemann rearrangement theorem, it really shows us just how poorly behaved conditionally convergent series are. Now, in part, this is just a consequence of how we define series convergence. You might think this is so bad that we really shouldn't even think of these as convergent series. Well, that would require us to then define convergence of a series in a different way. Um, we could do that. That would have trade-offs, right? But the way that mathematicians have decided to define series convergence, which is convergence of the sequence of partial sums of the series, necessarily means that these conditionally convergent series are still convergent, even though they can be very badly behaved. If you ever find yourself teaching, say, a Calc 2 course, right, it's sort of important to have in the back of your mind, anytime you're dealing with a conditionally convergent series, that you're not going to be able to use the normal sort of arithmetic tricks, and not even tricks, they're really just properties of arithmetic, right? You're not going to be able to use sort of commutativity and associativity in the same way without changing the value of that series. And again, the really important thing to note, right, is that you could in fact rearrange these in such a way that they fail to converge at all. So for conditionally convergent series, the convergence is very much dependent on the order of the terms in the series. Again, with absolutely convergent series, that's not a problem. You can rearrange terms however you want, and you'll still converge to the same sum. So in terms of thinking about absolutely convergent series, right? If I have a series with all positive terms, if it converges, it is absolutely convergent. Why? Because the absolute value of each term is just the term itself. All the terms are positive. So series with all positive terms, they're always going to be absolutely convergent. They're going to be very nicely behaved. Some alternating series can be, as we've seen, absolutely convergent, in which case they're still very nicely behaved. However, when you have alternating series that are conditionally convergent, it's important to be very careful because as the Riemann rearrangement theorem shows, there can be a lot of very bad behavior there.